Hello, our users. In this video, I want to show you how to do causal analysis using R with the difference in difference method. So the DID, the difference in difference method, estimates the causal effects by comparing changes over time between treatment and control groups. It uses before and after differences in outcomes to isolate the treatment effect. The critical assumption is parallel trends, meaning both groups would follow similar outcome paths if untreated. Suitable for observational data where randomization is not possible. Controls for unobserved fixed differences between groups, but is sensitive to violations of assumptions. It's widely applied for policy evaluation and program impact analysis. So that's a brief review of this method. And the implementation of difference in difference method in R is a package called DID, okay, DID. So I already installed it, so I'm going to load the library, set a random seed. I will create an artificial data set here. So the individual per group will be 100. Time period, I'm saying 4 time periods. So it allows 2 groups, but multiple time periods. So group is 2. Then I'll create ID variables and for groups and time periods. And the group will be 0, 1. And control is 0, treated as 1. Okay. And period, I get 1, 2 time periods and repeat n times groups times. Create a treatment timing variable. Treated group gets treatment starting period 3. Okay. So this G is if else group equal to 1 equals 3 and 0. Okay. Simulate outcomes with group time and treatment effects. So assume this formula applies for any group, any time, and any treatment effects here. Okay, so it's y is equal to 5 plus 2 times group plus 1.5 times the period, and then plus 4 times parenthesis period greater than equal to g and g greater than 0, then plus a random noise R norm. It's normally distributed with n times groups times time period. And then we put them all together in a data frame, and this is the data frame look like. ID period group, and then G, and then you get the outcome, okay? All right, so first we want to do is we can run the DID estimation using the function ATT underscore GT, group time average treatment effects. And this ATT GT stands for average treatment effect on the treated. More specifically, it's within the ATT GT output. The ATT refers to group time average treatment effect. Or it is the same as the estimated causal impact of the treatment for each group G at the time period T. Okay. So the syntax is you get ATT underscore GT, all the output will be saved in the object ATT underscore GT underscore RES. So you do that, then you have Y name equal to Y, T name equal to period, ID name equal to ID, G name is the G group, and data equal to data underscore did. Control group is called not yet treated, and estimation period method is DR doubly robust estimation, pen will equal to false. Okay. Once you fit that, you can see it is give you this output. First the call for fitting the model, and it also tells you the references Callaway, Brantley, and Pedro, Santana, and the difference in difference with multiple time period on the Journal of Econometrics. And then you see this group time average treatment effects. You get the time period, you get the group. So this group is not the treatment versus control group. Okay. So you got three groups. So you basically compare the zero, compare time 1 with 2, 3, and 4. Okay. And for each time, you'll get an ATT-GT estimate. You'll get a standard error estimate. You get a 95% confidence interval, simultaneous confidence band. Okay, so it's actually adjusted for the multiple comparison. So you can see the ATT for time 2 is a negative, and also then for times 3 and 4, they become all positive, and they're all significant. So time 2, you get a negative, maybe indicating the initial differences in the two groups. Then over longer time period in 3 and 4, you get a positive effect, which is statistically significant. Okay. And you see this p-value is 0.00513, so it's small. So this is saying the parallel trend assumption is not valid with data. So we really cannot completely trust this output, but it's beyond the scope of this video to dig into. So what we're going to do when this parallel trend assumption is not valid. There's another R package called HonestDid. So I provide the link here. You can check it out. I didn't look into it in details, so I'm not sure how well it works to adjust. I think it performs some kind of a sensitivity analysis. Okay. All right. In addition to the previous main output, we can also aggregate results by type. For example, dynamic effects over time, since treatment. The dynamic aggregate computes the average treatment effects relative to the length of exposure to treatment. We call event time. So this is very closely similar to like event analysis. So we get an event, the time to event. Okay. So to aggregate that, the ATTs in that way, we use the AGGTE. Then we put that ATT underscore GT underscore rest object there, and then we say type into the dynamic. Okay. So you can see it to estimate, it pull everything together based on the event time. And then you get ATT 4.1539, standard errors, and 95% confidence intervals. Okay. And then you can also aggregate by group, which is you detail the group time average treatment effects estimated by ATT underscore GT by group defined by their treatment timing. So this is the capital G. Okay, so that's so here you get aggregate TE, you put in that object ATT underscore GT and the rest, type of the group, and then it aggregate that way by group. You can see the aggregated ATT is also 4.1539. Okay. And we can also aggregate results by calendar time. So if you ask what's the difference between calendar time and event time, so the calendar time is the real world clock time in the calendar. For example, during data collection, you use year, month, or day. So that's the calendar time. Event time is relative to a specific event, for example, intervention, when intervention occurs. Okay, so 0 period after intervention or 1 period of intervention, etc. Okay, so if we do that, we can just use the type of the calendar option, and you can see the aggregated ATT in this way is also 4.1539. Okay, so you may ask why all three estimates, aggregate ATT estimates, are the same. That's because in our data, there's no difference in group size, in like time points. So these ADT estimates can be different if there's something happen, for example, heterogeneous treatment effects across groups, or time, or different group sizes. Now we have equal group sizes, but if you have one group has larger size than the other, these aggregated ADT estimates should be different. Okay. All right. I hope this serves as an introduction to the difference in difference method using R. Thanks for watching.